In this section, we will be learning about the different kinds of graphs. The information in a frequency distribution table can usually be presented more clearly and dramatically in the form of a graph. A typical graph is made with two perpendicular lines, one horizontal and the other vertical. The values of some variable are marked off along the horizontal line, which is also called the horizontal axis or the x-axis. A second variable, labeled y, is marked off along the vertical axis or the y-axis. When graphing a frequency distribution table, the variable of interest, like for example, the quiz scores, is placed along the x-axis, and the distance, like the height, would be along the y-axis, which represents the frequency count for each variable. Now, the simplest type of graph is the bar graph. You can see it in the figure on the left. This is a graph in which a rectangle or a bar is erected above each value of the x. In this example, you are seeing the size of the family. The higher the frequency of that value, the greater is the height of the bar. And the bar graph is appropriate when the values of the x come from a discrete rather than a continuous scale. As you may remember, in chapter 1, we were able to discuss about the difference of the discrete data to that of a continuous data or scale. We have learned that a discrete data or scale pertains to the measure that are not easy to change, or we always deal with whole numbers. Rather than continuous scale, they are bound to change from time to time, and we would also be dealing with fractional values in the continuous data or scale. A good example of a variable that always produces discrete values is family size. In our example, just imagine that the table shows not quiz scores but the sizes of the family. We are dealing with the number of parents plus the number of children. They are a total of 25 randomly selected families in which the parents have been taking fertility drugs. The bar graph on the left for these data shows that the bars do not touch, so we wouldn't want to give the impression that the values come from a continuous scale. That a family can be, for instance, between 3 and 4 in size. Now, a slightly different type of graph is more appropriate if the variable that is measured is a continuous scale. A good example of a variable that is always measured on a continuous scale is height. Unlike family size, height varies continuously, and it is often represented in terms of fractional values. A bar graph on a continuous scale in which bars touch each other is called a frequency histogram. For some purposes, researchers find the bars of a histogram to be distracting, and they prefer an alternative format, which is the frequency polygon. An easy way to think of a frequency polygon is to imagine placing a dot in the middle of the top of each bar in a histogram and connecting the dots with straight lines. Notice in the example that the frequency polygon is connected to the horizontal axis at the high end by a straight line from the bar representing the frequency count of the highest values and is similarly connected at the low end. Thus, the area enclosed by the polygon is clearly defined and can be used in many ways to comparing two overlapping distributions on the same graph. In the example, we assume that the x values represent inches above 5 feet for a group of 25 women whose heights have been measured. In this case, a value of 2 represents 5 feet 2 inches or 62 inches. 3 is 5 feet 3 inches or 63 inches, and etc. So whether your polygon is based on a simple or relative frequency, it is easy to find the mode of your distribution from looking at the polygon. The mode is the score on the x-axis that is directly under the highest point of the polygon. In our example, 6 could be the mode in this data that we are dealing with. And because the height of the polygon at each point represents the frequency of the score below it, the scores at which the polygon is the most popular score in the distribution, and therefore it is the mode. However, as mentioned before, there can be more than one mode in a distribution. Now let's move to the cumulative frequency polygon. A cumulative frequency polygon, also called an ogive, has a very different shape than a simple frequency polygon does. For one thing, the cumulative frequency polygon never slopes downward as you move to the right in the graph. Try to look at the example. That is because the cumulative frequency can never decrease. It can stay the same if the next value has a zero frequency, but there are no negative frequency counts. So a cumulative frequency can never go down as the number of values increases. This is the case for which the polygon is definitely easier to look at and interpret than the corresponding histogram. Notice that in the cumulative frequency polygon, the dots of the graph are not centered above the values being counted, but rather are above the upper real limit of each value. So in the example, we have 5 feet 1/4 inches instead of 5 feet 4 inches. So the rationale is that to make sure that you have the accumulated, for instance, all of the heights labeled 5 feet 4 inches, you have to include all measurements up to 5 feet 4.5 inches. The ogive can be quite useful when the percentile rank or the PR in which you are interested falls between two of the entries in a table. In these common cases, expressing the y-axis of the ogive in terms of cumulative percentages can help you to estimate the intermediate value that you are seeking. In the example table, you would need only to multiply the frequencies on the y-axis by 4, or if you could remember, we need to also divide the frequency by the total number of scores in our data or distribution table. And that is to create a cumulative percentage polygon. Then to find the percentile rank of any score, you first find the score on the x-axis of the polygon. Draw a vertical line from that score up to intersect the cumulative polygon, and finally draw a horizontal line from the point of the intersection to the y-axis. The percentage at the point where the horizontal line intersects the y-axis is the percentile rank of the score in question. So in the table example that we have, if you look at the x-axis and search for the score of 6, move up until you hit the curve, and then move to the left, you will hit the vertical axis near the frequency of 10. So here in our example, if you may follow the cursor, so from the point of 6 in the x-axis, and if you will try to look for it here and check the left or the y-axis, it is, or 6 is closer to 10. And this PR or percentile rank corresponds to 40%. So how were you able to say that 6 is about 40% in our frequency distribution? Always remember that our frequency should be divided over the total number of score entries, or n. So in this case, if you try to check on 6 at the x-axis, it is equivalent, somehow it intersects with the score or frequency 10, and following the formula, which is frequency over n, 10 divided by 25 is actually about 40 or 40% as a percentile rank if we are talking about 6 as our height in our example. So to be more specific, the 6 inches height is equivalent to also having 10 as a frequency, and we may recall with the formula that we have, 10 over 25 is equal to 40, and that is our percentile rank, which is 40%.